My name is Devin Petersohn. I'm a grad student in the RISE lab, and I'm here to talk about Modin, which is a drop-in replacement for pandas that effectively lets you scale your workflows without needing any additional computation knowledge in the distributed area. The title of my talk is Scaling the Capabilities of the Data Scientist, Not the Machine. Effectively what that means is lowering the barrier to having to do distributed computation. So to kind of frame the problem, I want to talk about what I call the data science landscape. This is kind of what people are doing with data these days and how they're using tools. So here on the left we have tools that are efficient for data sets that are on the order of a megabyte, maybe a couple of gigabytes. And these are really solid tools. On the right here we have tools that are being used to process hundreds of gigabytes plus. These are also great tools that do what they're supposed to. But there's a disconnect here. There's a gap and a learning curve between going from the left and going to the right. So tools for small data, they typically follow these programming styles that you're comfortable with in Python. And they're really widely understood and used. So if you run into problems, you can just type into Google what your error message is, and you'll get loads of Stack Overflow. Stack Overflow posts about the same problem, and you can read the answers and get really, really solid advice for what to do. Additionally, the majority of college graduates will graduate knowing these tools. That means that, they understand how to use them whenever they're going into the field. And this is how we actually teach data sciences with these tools. There is a problem, though, and that is the no scalability. Basically, most of these tools are single node, single core, in fact. On the right, when you talk about tools that are efficient for this larger data, we start running into problems with debuggability. This debuggability can be in terms of performance, right? Your job might take significantly longer than you expected, and you have to dig into the logs to figure out why. There's also the debuggability when it comes to actually bugs that you yourself wrote. So if you wrote a bug, a lot of these things come with like giant stacks of like JVM stack traces, and you got to dig through them, and it can be really cumbersome for, especially for people who are much more comfortable with, the left side. A lot of them also require distributed computing knowledge, so understanding partitioning. A lot of systems actually will punish you if you don't know how to partition your data well. And lazy evaluation is also really commonly hated by people who are interacting with their data. A lot of this comes down to the fact that, back to debuggability, you might find out 20 lines ago or 20 lines later that your line of code actually had a bug in it, but 3 hours later, you're finding that out. Additionally, it was designed by systems people for systems people. So systems people really understand systems, and they want these tuning knobs. So they design these systems to have these knobs to be able to tune. But they also present new APIs that effectively do the same thing that you would do on smaller data. And so we get this problem where tools on the left are usable but not scalable, and tools on the right, I don't mean to pick on Spark too much, but because it is a great tool, but tools on the right are scalable but not as usable. And so we run into this problem a lot of the time where a data scientist will work with some sample data to get some general knowledge about their data, and they'll use pandas on it. But then when they want to do literally the exact same thing, literally the exact same query, they have to rewrite the entire thing to run as a Spark job.
I thought pandas ran on top of Spark.
Pandas does not run on top of Spark. Save your question, I'll answer. I know what you're talking about, save your question. How? We'll get there. Okay. So Modin is a project that we created here in the RISE lab to kind of bridge the gap and get rid of all these extra requirements that we have on the right. And so now, because at the moment we expose the pandas API, we have things that are usable and scalable, but also scalable and usable. So the pandas API is incredibly massive. There are challenges in integrating something like this, and I kind of want to take a few minutes to talk a little bit about the pandas API because recently, even in the pandas community, there's been a lot of discussion about, potentially changing some things. So the API is massive. DataFrame has 280 methods. A lot of these things do the same things as each other, and they're there for convenience. It's not necessarily some giant API bug. I mean, it's the most used DataFrame library for a reason, because it's so expressive. So combined in total, we have over 600 APIs that need to be, worked on. And so we had this idea: what are people actually using in pandas, and how can we go about implementing these things potentially in the order that people are using these to have the highest impact? And so we did a study scraping Kaggle notebooks. The study, all the data and the notebooks and everything can be found at that URL. These slides, I'll post them to the Slack channel after this. But you can find everything at that URL. And basically, effectively what we see here is that it's not just SQL operations that people are using. There are things from linear algebra that people are using, and there are also some spreadsheet operators like pivot table and things like that. And so with Modin, you can scale your pandas workflows by changing one line of code. It's a drop-in replacement, so of course the one line of code is the import statement. You just replace that import pandas with import modin.pandas as PD. And then everything should just work as is. And you should expect the same behaviors. We actually take this so seriously that we also give the same error messages, with, even if there's not necessarily that good of a description in the error message, we give that as well. But we just want to make sure that literally the same behavior that you would expect is what you would see in Modin as well. We upload to PyPI, so you can pip install it. And you may ask yourself, how do we speed things up? Well, if you take a look at this, unfortunately very white, it's color on my desktop, but we have this modern laptop, we'll call it. Modern laptops come with multiple CPUs, and a lot of times data scientists are just interested in getting faster computation, even just on their laptops. And so when we look at a pandas data frame, the pandas data frame is, well, first of all, it really only works if the data fits in memory. And we see here that it's working on a single CPU. With Modin, I'll talk a little bit more about memory, because we don't necessarily have the requirement that everything fits in memory, but we also can use all 4 of your cores. So you may think, oh, okay, well, 4 cores is not that much. Maybe it's an extra, a few milliseconds or something like that on my computation. But whenever you want to start working with larger data on a large machine, we start seeing this problem, get much, much more significant, because the Modin data frame is going to be able to use all of these cores. And so read-CSV is basically the most commonly used data ingest method of pandas, and it's also one of the biggest bottlenecks. It usually takes significantly longer than any individual computation that you do after that. Primarily that's because of the parsing involved in read-CSV. And pandas has a really good CSV parser. The CSV parser is really robust, but since it's working on a single core, it's not necessarily fast. So what we did is we took a machine that we have access to in the RISE lab that has 140 cores, and we tried to see, what kind of performance we can just get just by reading, ignoring distributed file systems and all of these fancy new things that we're used to. Let's just take one CSV file and see how fast we can read it. And so we basically, the high point here is that we can get more than 1 gigabyte per second of read and parse throughput. So your giant files that were taking 10 minutes to read before, right, 5 minutes, they're taking seconds. And so I'm also presenting here a more realistic benchmark, because most people don't really have access to 140 cores, or if they spin something up in EC2, it's an exceptionally expensive instance. So 16 cores is a lot more reasonable, though. There are a lot of workstations that have this. So we took a look at a 250 gigabyte data set. We wanted to load it in and basically have it exceed the memory. So this is a kind of a conversation about out of core, which is another issue that pandas has, where exceeding memory becomes kind of an issue. You don't always have enough memory to fit your several gigabytes file. So with 32 gigabytes of memory and 16 cores, we can read with roughly 1.7x overhead, being able to swap to disk and things like that, versus having a giant pool of memory, a terabyte of memory. We get this kind of only 1.7x speed up, which if you know the latencies of going to disk, that's pretty significant. So with the last few minutes that I have, I kind of want to talk a bit about the Modin architecture and like how we've gone about designing the system, because it's intended to be abstracted away so that different pieces can be added to or improved or enhanced along the way. So at the top layer, we have the API layer, and we expose pandas. I have this kind of proof of concept SQLite just to show that it's possible. And then there's this Modin API, which I'll talk a little bit more about when we get to the DataFrame, the Modin DataFrame. It's basically exposing what our internal API is. So the query compiler layer is effectively a layer that kind of translate this. It translates this large pandas API and all these behaviors into a small subset of behaviors that basically enforces that there's only one way to run any given behavior or any given operation. I put this green box here, which is bring your distributed data frame. That is basically like, that's another purpose that the query compiler serves, is that if you have a data frame implementation, if you implement this query compiler interface, you can actually get all the benefits of having this pandas API with all the error checking and all these error messages and things that we've spent a while, making robust. You just implement that interface and it should just work. So onto the Modin DataFrame. The Modin DataFrame is basically our main abstraction, and it is the minified API or the kernel of pandas operations. You may know that DataFrame operations are not just SQL operations. They encompass linear algebra, as I said earlier, and also some spreadsheet operators or things like this. And it's very like what you see is what you get. You're interacting with it. You're looking at the data often. And so taking these core principles, we built this main abstraction, and there's a lot more information in the documentation that lays out like the API and like what each of the APIs does and kind of encompasses. Also in the tutorials, you'll get to be able to register some custom functionality with the query compiler that interacts with the Modin DataFrame API itself. And then at the bottom layer, as I mentioned, everything is abstracted away such that we can plug in different components and use them, because different people may have access to different types of machines or things like that. So Ray is basically where we started, and that is by far the most robust implementation. We've also implemented Dask, and that's mainly for Windows users at the moment. And it's still kind of in an experimental phase a little bit. And then we also have a pure Python backend that basically would inform new users who want to add these kind of task parallel-like systems, something, maybe you want to do some generic multiprocessing or MPI or something like that. This would kind of inform you what interface to implement and then like kind of how it should look. And so that at a high level is the architecture. I'm definitely happy to go much, much deeper into detail, one-on-one, but it's after lunch and I don't want everybody to fall asleep. So with that, I'll kind of close a little bit. Can we get a mic? Okay, sorry, I didn't hear. Yeah, so the data is partitioned. We're doing that. Yeah, so we do that basically on ingest. So if we get back to here, so the Modin DataFrame is actually kind of the abstraction that's in charge of like distributing the data. If you implemented some other distributed data frame, you would also be, that abstraction would also be required to kind of handle the partitioning, if that makes sense. Yeah, so the question is, sorry, I didn't repeat the question earlier. The question is, how do you distribute the data or how do you split the data into chunks? Most of the time that's happening on ingest. Most people, this will be covered a little bit in the tutorials as well, but most people are not creating data frames from like just regular NumPy arrays that they have kind of lying around or some sample data. Most people actually have their data on disk in some file format. And so the way that it's partitioned is actually by like on ingest, effectively. So whenever we're reading the file, we're reading parts of the file into the partitions, and then we keep them separate. Yeah.
So I'll speak louder. Everyone can hear me. The hot thing when you talk to anyone working with pandas today is Arrow.
Yeah.
And even West McKinney behind pandas is now pushing Arrow.
Yeah.
Do you see yourself as a competitor to Arrow? Do you see yourself as complementary? How do you see yourself fitting in there?
Yeah, so definitely not a competitor. I actually have some backup slides because I was expecting a question like this. So, so Arrow, they're actually, there's this table format. It's an in-memory format that basically allows you to go across languages with no copying, and it's a really fantastic project. If you haven't heard of it, I definitely recommend looking into it. As a part of the Arrow project, they're actually building some compute kernels. So I mentioned before how Modin is abstract. We can basically plug these compute kernels in at the right point, and we can gain the performance benefits of having these as a part of things. And Arrow is not kind of a distributed system, if that makes sense. So we're basically distributing the computation of Arrow in this case. So it's definitely not some kind of competition in any sense of the word, but it's more along the lines of like they're producing these really high quality, really fast compute kernels, and we're abstracted in such a way that we can actually plug them in and use them.
So many of us in the industry are looking to Arrow as a common in-memory data format.
Yeah.
Do you have your own in-memory data format?
No.
Or do you see yourself adopting Arrow?
We would adopt Arrow. So right now, our in-memory format is kind of pandas. Like we treat pandas as a black box where we can operate on it on these partitions individually, and that's our in-memory format. That is obviously not our long-term solution. Arrow will fit that and solve that problem very well. So yes. Yes. Yeah, so good question. The question is, when you run Modin on Ray, is it still using Ray's in-memory object store, or can you also use streaming data? The answer is that it's using the in-memory object store. It's not impossible to build a kind of a streaming, like a way of dealing with streams of data in Modin. Thus far, it's more or less been kind of a lack of time. Time is the ultimate challenge, I guess. Okay, there were some like high level kind of overview points that I wanted to get to, and then we'll go back to questions if there are any. But we're still working on cluster support. We're working very closely with the Ray team to kind of get this, to get things to continue to be nice, basically. There's a reason why these systems chose to have all these distributed computing abstractions exposed to the user. We want to make that so that it's not required in the cluster setting to choose partitioning and things like that. There's additional research that we're working on basically to perfect that. We have a developer mailing list. You can also join. There are links to this on the GitHub repo as well, the documentation. We put basically as much as we can on the documentation. There's architecture, all sorts of low-level information for people who are interested in kind of extending Modin in one way or another. So yeah, are there any other questions? Yes, in the back.
In terms of how much resources Modin uses, is that like config? Does it greedily just get everything it finds? Like in the example you had with like all the CPUs being not idle.
Yeah. So So it will use all of the resources that Ray, so talking about like the Ray backend, it will use all the resources that Ray exposes through its API. So if you start Ray with fewer CPUs, then we will use those fewer CPUs, if that answers your question. So yeah. There's information on the documentation on how to do that as well if you have questions. So. Okay, thank you all so much. I'll be wandering around a bit. If you go to rise.camp, you can just click on the Modin tutorial. That should take you directly to the notebooks, and then the exercises are ordered. So, yeah, thank you. Sorry?